Welcome to Chemistry, Chapter 1, Section 3. This is the last of a three-part video series which covers Chapter 1 of our current textbook, which really introduces chemistry and talks about the classification of matter. This is, I believe, a slide presentation turned into a video with narration, and this lasts, I believe, 24 slides, including the title slide here. Okay, Chapter 1, Section 3, the elements. Of course, you've already recorded some of the information on the student learning map. Remember that the unit essential question shown below here is on your test. And if you understand from section 2 that matter classification chart as a graphic organizer and can explain it, you pretty much have the answer to that question in the bag. Although you want to also say why, how do and why do the chemists do that. Now for the last lesson, lesson number 3, it will coordinate with section 3, and that will be matter and the elements. The question here, how are metals, nonmetals, and metalloids different, and where are they found on the periodic table? Now I do understand that that is really two questions in one, but because it addresses all aspects of those three types of elements, I just eliminated the need for two separate questions. If you need to remember at any point, you can pause a slide to get the information down. Please record all of this information in your notes. You should pre-read the section before you actually take the notes on it. You will get way more out of this presentation. And if at any point you feel the need to mute because it's getting in the way of you taking notes, or you can take the notes without the narration, that's certainly fine. I'm not there to control it. But I will do my best to explain what is the information around the slide and what is on the slide, because this presentation is not necessarily standalone. This is why the narration exists. If I'm in class, I'm helping to narrate, and certainly I'm here narrating. It is just not meant to be a standalone where the slides explain everything by themselves. Really, the standalone is your textbook. You read the section, that's essentially standalone. That'll give you all the information you need. Okay, the objectives for this particular section. I do not see any asterisks or stars with these objectives, and so this tells me they come right directly out of your chapter. This is a great source for test questions, and so you should pause and write them down, or get into your book and write them down, maybe leaving a gap in your notes to go back and do that. That's up to you, but I strongly recommend you write them down. Great test questions. Okay, this particular slide here is just to announce what I'm saying is the first quiz that we will take on, or a quiz on the first 20 elements. Now the first 20 elements on the periodic table start in the upper left-hand corner with the element hydrogen, and hydrogen is number 1 on the periodic table. And this quiz will go all the way through calcium, which is element number 20, thus the first 20. What would you want to know? The name correctly spelled, and the symbol correctly written, meaning capitalized and lowercase as necessary. And you would also want to know the atomic number 1, 2, 3 all the way to 20. So this quiz, when will it be? I, of course, will not announce a date on this particular slide or in this presentation, because I don't know when you will be watching this presentation. So I will announce this in class when it is appropriate. Most likely these quizzes will occur during Chapter 2, not necessarily Chapter 1. And we will actually take multiple quizzes. While we will not memorize the entire periodic table, we will memorize a few of the elements. This is only the first of a series of, I think, 3 quizzes that we will take where we memorize some of the elements so we become familiar with the periodic table. But they will all be pretty much like this. They're not very hard to do in order to memorize those for most people. Okay, so here is a version of the periodic table. Now this is out of date, and I know it is out of date because if you look at the very bottom, or not the very bottom, but kind of the one of the lower rows here. So let me get a pen color that's going to show up. So this row right here. So this row is row 7. This is row 6, goes all the way up row 7. By the way, this is part of row 6 and row 7 as well. These two go right in here. If you notice, it goes 57 to 72. Here's 58 all the way to 71. Here's 89 to 104. There's number 90, 91, etc. So these are just parts of those two rows pulled out at the bottom. But if I look at row 7, period, it's called period 7 really. Period is the official title of that row, of a row. But period 7, row 7, notice we have everything is filled out here, everything's filled out here, but when we hit here, 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 this box is even missing. Here, 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 and here. The current periodic table has all of these boxes filled in with their actual names and symbols. So this image is actually out of date, but it really doesn't matter for the purposes of our discussion for the periodic table that it is out of date. Just realize that all of the images, well, I use this image multiple times, that it is out of date. So what do I have circled here? Well, I have the, in the upper left-hand corner, right up here, I have the number 1 circled for hydrogen. Over at the right hand side over here I have the 2 circled for helium, and then of course way at the bottom you see number 116 circled for that particular element there. So with that being circled, what does that mean? Let's check the next slide out. Those circles on that previous periodic table are actually referring to the atomic number, which is how the modern periodic table ever since the early 1920s has been arranged from low to high, 1 to whatever the higher number was. Nowadays the highest number is 118. That very last box from the previous mentioning would be filled in. So it's the atomic number. Well, what is the atomic number? It is the actual identity of the element. So hydrogen is number 1. That number 1 being the atomic number is the identity of what it means to be hydrogen. But what is atomic number? Well, it's actually the number of protons. If you see this second bullet down here, it's actually the number of protons found in the nucleus of that atom. So hydrogen has 1 proton. P+, that's a symbol for a proton in its nucleus, whereas helium has 2 protons in its nucleus. Lithium has 3 protons in its nucleus, and beryllium has 4 protons, all the way down to element 118, which would have 118 protons in the nucleus. So that's how the periodic table is arranged, and that's how we tell what elements are what. It is literally their identity. And this is why alchemists, from back when we were talking about alchemists a little bit, they were always destined to fail to trying to turn things into gold. Because if you want to turn anything into gold, you actually have to have 79 protons in the nucleus. Until you have 79 protons in the nucleus, you do not have gold, and they have, and we actually do not have a great ability to do this now, but they had no ability to affect the nucleus of any atom in any way, shape, or form. It was just impossible according to the tools that they had, and it's very difficult for us given our level of tools. In the future, it may be very simple. It may be child's play in 200 years, but right now, it is not simple, but it is not impossible. Okay, now looking at this periodic table, again the same out-of-date periodic table, but it's still functional. Notice I am circling the up and down columns, the up and down columns. The columns I have chosen are not particularly important. It's just I'm circling columns, up and down columns. What are columns? Columns are actually called groups on the periodic table, and sometimes they are referred to as families instead. Whether you call it a group or a family, you got it. They're both interchangeable for the periodic table. But the periodic table has 18 vertical columns. Each of these columns is unique in that the elements that are grouped within that column all would typically have similar characteristics in some way, shape, or form. That's why they're grouped together. Very much like me and my family. If you look at my children, they actually resemble my wife and myself because they have our DNA, of course. And so we are a family in that respect because we all actually are very closely related. And so we have very similar characteristics. So that would be why the word families is actually used here, but I typically call them groups myself personally. There are 18 of them. Now on this periodic table image, I have circled the rows, but before I go to the rows and talk about that, let me talk about the columns one more time. I have a pen activated. Let me get a color that'll show up. And if I look at the up and down columns and I number them, this would actually be column number 1 or group 1. This is group 2. Down there would be group 3, group 4, group 5, group 6, group 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. That's where the 18 comes from. Now there is an older system, and you see it here like 3A, 4A, and all of that. That's an older system that is not widely used anymore. And because it's not widely used, I ignore it when it's on a periodic table. Sometimes you'll see Roman numerals and A's and B's on periodic tables. There again, it's an older system and it's not really utilized very much anymore. And guaranteed when you go to college, you're going to use the 1 through 18 numbering system. Okay, let's move on with this one though. Excuse me. So this one actually is circling the rows. The rows, of which there are actually 7, we kind of started to count them the other time here. If I can count them here and number them, 1, row 2, row 3, row 4, 5, 6, and 7. And remember in here and here that we have here and then there, this is still parts of row 6 and still parts of row 7. Now the rows that I circled are not, they're just to circle rows, they're not any particular thing about a row. What are the rows? Well, the rows are technically called periods, of which there are 7 of them on the modern periodic table when it's numbered to 118. So that last element there, 118. Each row has properties of elements that are arranged by how they change. So they're not really similar to each other, but they are changing in some sort of kind of patterned and predictable way. Typically, we read the patterns from left to right, and if you go from left to right, they start more metallic and they become less and less metallic as you go from the left more to the right-hand side of the periodic table. Remember that rows 6 and 7 are extra long, and because of that, we've actually taken, most periodic tables have those rows partially taken out and put at the bottom, but it's just extra row 6 and 7. They do that to keep the physical periodic table smaller. So here is a copy of a full long form or full form periodic table. Notice that they've actually then gone and included those 2 rows, now put back in where they should go, right there. However, even when you see it in the long form, there are still only 18 truly recognized columns from 1 to 2, and then over here to 3, finally up to 13, and eventually 18. There are no column numbers given for any of this. So they don't actually extend that at all for that. It's just 7 rows currently and 18 columns. Now over here, this element is actually the last one we have right now. It's element 118. If we develop 119, if we find it, when we find it, then it's going to go down here for 119. That's where it would actually go, and it would start an entire new row. Updates. Every once in a while, atomic masses and other types of information are updated on the periodic table. It's by no means 100% complete because we are always discovering new things, albeit very slowly. So, once in a while we need updated periodic tables. So if you go back and you start looking at periodic tables from 20 years ago, from 40 years ago, and comparing it to the one I gave you in class, then you would see some of those changes. They're subtle, but you would see some of them. The bigger changes, of course, are when elements are actually added to the periodic table, like 113, 115, 118, etc. So currently, all the elements numbered from 1 through 118 are on the most up-to-date periodic tables because the governing body, if you will, for chemistry that is able to officially decide these things for worldwide chemistry is called IUPAC, and they have officially recognized all 118 elements at this point. And IUPAC stands for the International Union of Pure and Applied Chemists. And it's a group of chemists that are, I believe, elected into positions, and they serve terms just like a government, and they officially decide things that are chemistry. Most sciences have some sort of an official governing body like that to make official designations. Interestingly, what would happen when we discover element 119 or 120 or 121 is, of course, we start making new rows on the periodic table. Okay, now what I have on this periodic table is a dividing line. And that dividing line is actually going to divide kind of a very large left-handed section with a very much smaller right-handed section. And that really is looking at, in this case, on this side are all of the metals, and this side are all of the nonmetals. And then around this, down through here, are a kind of an intermediate compound called the metalloids. The metalloids. So let's see what we have. Okay, so what does it mean to be a metal? And most elements on the periodic table are actually metals. So what does it mean for any element to be a metal? Well, all metals will have luster, meaning that they can be shined. They can actually be shiny and reflective. You may have to polish it, but it can be shiny and reflective. Metals all have high melting points and are solid at room temperature except mercury. So actually let's just, mercury is the one exception to that. So except mercury. So mercury, Hg, comes from the word hydrogyrum, which is Greek, I think, or actually it's Latin, for mercury. But mercury is actually a liquid at room temperature, but otherwise everything else is a solid. Metals have higher densities. They're heavier, unit per unit. They are malleable and ductile. Malleable means that it can be hammered into a thin sheet and molded and worked with. And ductile means that you can thin a metal out and make a wire out of it. So wire making. Metals will conduct heat very easily, and they will conduct electricity very well. Now, not all metals conduct electricity equally. Some do it better than others, but they all do them well. Metals tend to lose E-. That is a symbol for an electron. Metals tend to lose electrons when bonding to Nm, nonmetals. And so metals just give their electrons away to nonmetals during bonding events. Okay, moving on to this, we are back to the dividing line again. And if we just talked about metals, then what we'll do is we'll then talk about nonmetals, which are the elements over here. Now, by the way, this includes hydrogen. So hydrogen actually is a nonmetal. It's put over there for a particular reason on the left-hand side, but it's actually considered to be a nonmetal. So let's talk about the nonmetals. Essentially, if you want to know the property of a nonmetal, take the properties of metals and just assume the opposite. So, metals are very dull in appearance. They are non-lustrous. Metals have low melting points. Matter of fact, some melting points are so low that the nonmetals are already gases at room temperature, like nitrogen and oxygen, which we are breathing. Metals, or nonmetals, excuse me, have low densities. They're not really heavy. Nonmetals, if they are solid, are very brittle, so you cannot hammer them, you cannot create wires out of them, you can't make them into thin sheets, so we consider them non-malleable and non-ductile. And if they are solids, they are very brittle when solid. So if you strike them, they would just shatter. Nonmetals are very poor conductors of heat and electricity, so much so that oftentimes they are actually called insulators. Whereas metals are called conductors, nonmetals are called insulators, the opposite. Will they conduct heat and electricity? A little bit, a little bit. They're not like non-conductors, they're simply very poor conductors. And that's a distinction that you would want to make. And lastly, if they are going to interact with metals, they would gain electrons during a reaction, during a bonding event with a metal, and they would gain the electrons that the metals lose. And when metals lose and nonmetals gain, it forms a natural attraction between the two opposites, and that's where the bond forms. Okay, now I've taken the periodic table and I've replaced that dividing line with some circles. Matter of fact, there are exactly 6 circles. And those 6 circles actually outline from, in order, they outline the element boron, silicon, germanium, arsenic, antimony, and tellurium. And antimony has this SB, but that comes from stibdinum or stibium, again, a Latin name that we now call antimony. But it's these 6 elements that actually form kind of like a stair step, if you will. Or maybe the stair step goes like that. It really depends on where you look at it. But it forms the dividing line between metals and nonmetals, and it forms the metalloids. So the metalloids, I would commit to memory: boron, silicon, germanium, arsenic, antimony, and tellurium. If you memorize those 6, you know the dividing line. And if you know the dividing line, to the left of that, all of those elements, a bunch of them, are metals. And to the right are nonmetals, a much smaller set, including hydrogen. You just have to remember hydrogen. So what about the properties of what makes up a metalloid? Well, these 6 elements are semi-lustrous. They're a little bit shinier than nonmetals, but they're a lot duller than metals. They are solid at room temperature, but it doesn't take much temperature to get them to melt. So they are solid, but with low melting points. They are semi-malleable and semi-ductile, so you can work them a little bit. So you get them to thin down by hammering them. You can get them to thin out a little bit if you pull them, but to a point, and then they break. So they are semi-malleable, semi-ductile. One of the main properties that has been of very big use to the world, literally, for metalloids is their ability to regulate the flow of heat and specifically electricity. So they are semiconductors. So they let some electricity through, but not a lot, but more than metals, or more than nonmetals. And so they're semiconductors, and this has given rise to literally the computer industry for the past 50, 60 years and beyond. Okay, lastly, because we're getting very close here, we're on number 21 and 24. Now I have circled a column again, but this column is very specifically circled. This is column number 18. This is group number 18, and it includes the elements of helium, neon, argon, krypton, xenon, and radon. Collectively, that column of helium, neon, argon, krypton, xenon, and radon are called the noble gases, and it makes up group 18. So these 6 elements, and then oganesson actually, while not really, it's confirmed as an element, but it's not confirmed, I believe, necessarily as a noble gas, but the element, and I'm trying to activate a pen here, I'm sorry, I'm kind of talking over myself, but the element Og oganesson would be element 118. So technically it should be a noble gas, but we don't have enough of it to experiment with to figure it out. But the others are. What's the main properties of these noble gases to make them distinctive amongst all the other elements? Well, these 6, maybe 7 gases, certainly the 6, are very unreactive to the point of where we call them inert. They are very, very stable as they are born in nature, and they form no compounds. They don't interact with each other. They're just elements that exist. The reason why they are so stable is they have what are called stable electron arrangements. The number of electrons that orbit these atoms, specifically in the outermost orbits, because orbits are layered, there's a lot of layers of orbits. In the outermost layer of orbits, it's very stable. It's the perfect arrangement of electrons for an element. And only these 6 elements actually have that arrangement. All other elements have a different arrangement of electrons, which causes them to be unstable, and that's why they mostly form compounds, because the compounds typically are more stable than the elements were. Noble gases do not have that problem. So noble gases, because they don't react with anything, were very, very hard to discover, like the infamous white cat in a snowstorm or a black cat in a dark room, where you can't, if they're not making sounds, you can't find them. They're just difficult because they blend in. Well, these noble gases are like that. They just blend in, and they're very, very difficult to discover. But when they were discovered, it was proposed that because they were so unique, that they add an entire new column to the periodic table. And so that was a big deal. That was a big change when you added an entire column to a periodic table, and it became the column we now call the noble gases. And that's really for nobility, like how the nobility would not mix with the commoners in a kind of a king and queen society, and or like a monarchy, I guess I should call that. And so that's what kind of where the noble part of noble gases came from. Okay, lastly, this is the periodic table again, and remember that while this one is out of date, the last box there should be element 118. We have all those boxes. The periodic table I gave you in class has all those boxes. So this is it. That's the periodic table, and the last little bit of this section was certainly about metals, nonmetals, and metalloids, and then some basics before that of the periodic table itself, groups and families, and the periods, of course. Well, this is slide 23 of 24, and 24 comes up, and it's just the Pennsylvania standards again for reference. So I will say that this fairly concludes the entire presentation. And if you have any questions about this or any of the other two videos, if you watch those or anything in class, by all means, please see me and we will get those cleared up. Make sure that you've done any and all homework, and if you're starting to prepare for a test, that you remember you have a test study guide that you can study with, and the unit essential question will be on the test along with the definition of chemistry and the law of conservation of mass. Please make sure that you're using our our class definitions, because they are the most complete and they will earn you the most points, the maximum points on a testing situation. Thank you, and I look forward to the next presentation, which will be in the next chapter, chapter 2. Here are your standards, just to kind of wrap up the entire chapter. Here again, it's a standards-based class. Thank you. This is the end of the presentation.